So hello everyone, and welcome to another conversation of the fifth cycle of conversations on corporeal architecture. My name is Maria da Piedade Ferreira, and I am very glad and honored to introduce you today to Hugo Spiers. Hugo Spiers is Professor of Cognitive Neuroscience in the Department of Experimental Psychology at University College London, UK. He is a Fellow of the Royal Institute of Navigation and co-chair of the UK chapter of the Academy for Neuroscience for Architecture. His research explores how our brain constructs representations of the world and uses them to recall the past, navigate the present, and imagine the future. His research team uses a range of methods, including brain imaging, neuropsychological testing, virtual reality, and single-cell recording to understand brain function and spatial cognition. Hugo, thank you so much for accepting this invitation.
Thank you very much for inviting me to speak in this session. Yeah, it's an amazing sequence of talks you've had in the past and great topics. I'm really delighted to be here to talk about it. As I've mentioned already, just a warning that I need to jump to mute and sort out a small child in the background, my two children being sick here. But hopefully I'll get through most of what I'm planning to talk about. So I'm going to start my slides up and share some of the work we've been doing over the last 2 years in relation to that question. Let me get this working. Here we go. Yep, here we go. So, yeah, you should be able to see my title page. Is that right? It says,
yes.
Great. Okay, so very broad title for today's talk on spatial cognition, brain function architecture. And my training, my background is in neuroscience, and I got early in my career involved in studying how the brain represents space and uses it to navigate. Really, that's the foundation of what I've been doing in my career. But way back, in my sort of early postdoctoral years, became aware of this interest in architecture and how architects effectively have to think about the reverse problem. We're trying to work out how the brain encodes space, but architects have to plan the space and design it. And this is always interesting. And then 2005, I think it was, around that time, I started collaborating with an architect, Bettina Wiesmann from Germany, and a painter, Anthony Malinowski, who extensively, as a painter, had worked in architectural space. And we were funded to create an art exhibition in London that took on the idea of how does the brain represent space and architecture, and explored it through a film installation. And this is an installation called Neurotopographics, which had a whole lot of images. It's not really present anymore online. And I won't delve into that piece of artwork, but it was my sort of first foray into understanding a bit more about how architects think and how artists who work with architecture think differently. And the challenge of really trying to broadly think about that intersection between neuroscience and architecture. So I'm very glad now to be one of the co-chairs of the UK chapter for neuroscience and the Academy for Neuroscience and Architecture. But let me start with one of the studies. So many years later past, I set up my own lab, and I really specialized in human brain imaging, functional magnetic resonance imaging. And that's still a research tool of choice. So if you want to delve into how the brain represents architecture or space, you need to get into quite deep structures in the brain. And there's real excitement currently in mobile brain imaging, and I think that's going to take off significantly. Currently in 2023, it's still very difficult to really get at some of these deep structures we're interested in. And by deep structures, I mean the ones like in the middle of your head, pretty deep as in like you can knock towards the top of your scalp. So one study we devised to get at how does the brain represent the layout of a city. So how do we, as we pass through a city trying to get to somewhere, represent the spatial structure of what's there and what you can do, what's possible in the future, going into that introduction about future thinking in my lab. So what we did back in 2012 onwards to build a set of high definition video films, first person view video films of routes that weaved their way through the densest part of London. And the densest part of London streets is an area called Soho in London, which is really an old, it goes back to King Henry VIII's hunting ground, but became a really densely packed area of bars, and nightclubs and all sorts of things going on. But the key thing is the streets are really short and there's lots of options to navigate. It's a difficult place to navigate, but you know where you are because there's loads of landmarks. So as a neuroscientist interested in city structure and being able to get lots of activity in the brain doing things, Soho was the place of choice. So what we did was have people walk around for 2 hours and learn on day one the layout of Soho, or a small section of it really. We had them sort of tested on their knowledge after walking around taking this tour. And the idea was the next day they would lie in our brain scanner, which we can't move, it's fixed, but we would immerse them in this film we'd shot, these first-person view movies, and ask them to make choices at every junction in the movies. The movie would pause and ask them what to do. And then we could look at brain activity when you're thinking about where to go. When you're given a destination to get to, when you turn into a new street, when you get you have to take a detour, when all these things happen, how does the brain react and what's going on? So we looked at that. We published a number of studies on that data from recording people's brain activity with fMRI. But one of the key things we did was to collaborate with Beatrix Emo, who was a student of Ruth Dalton's at UCL, where where I'm based in the psychology department, over in the architecture department, have spent years developing space syntax from Hillier and others, and Alistair Turner is the big development of agents, and there's a whole history of space syntax there. So what we thought we'd do is to apply those methods to London. So here is a very bright colored image where every street segment, each identifiable section of the streets in central London, are colored in red by their topological proximity, closeness, centrality to the center, the topological center of London, which is probably somewhere in the middle of this map, like 7 Dials or somewhere. And you can see in black the River Thames snaking its way through London. You can see all the bridges are very red. So this is a metric called segment integration in space syntax, but mathematically is approximate to closeness, centrality, and graph theory. But effectively, it's a very simple calculation of how many steps does it take to go from a given street to the center of the network. So the streets that are in blue take many steps to get to the center. The ones in red, like Oxford Street, maybe 1 step, and you can arrive at the center of the network. That's one measure that people from space syntax have used to look at how people move and will congregate and explain the dwell of like where pedestrians will tend to move to and move around in spaces like museums and in city streets. And indeed, Trafalgar Square was redesigned using this method of space syntax in London to reconsider how it could be laid out better. But that's one measure. Here's another measure, which is betweenness centrality, where we're trying to quantify, in this case, how many times would you go through a given street going from one location to any other? So a lot of the streets in London are dark blue because you wouldn't go through them very often. But a lot of the bridges and the main roads like Oxford Street, you would use those streets regularly in terms of mathematics to progress from one point to another if you plot all the possible paths through the space. And this is known as choice in space syntax, or in graph theory, betweenness centrality. What's the betweenness measure? These are just quite simple measurements of space. And the simplest one of all is the degree centrality of the street network. And so this is just how many connections does a street have. So you can see right in the center, 7 Dials, there's 6 options leaving that little roundabout in London. But there's a lot of like one-way streets where if it's an L shape, the end of the L will be very low. There's only one way to leave that alleyway. And so it will have the lowest degree centrality, or connectivity is the word used in space syntax. So this is a field that I've been working and developing for some time. There's a whole space syntax conference. What we've done here is to take the small bit of London that we had our people trained on. They walked around this physically, learned it, and the next day watched movies, having to make choices about which way they would go at junctions during movies, snaking their way through the streets. And the movies took routes they'd never taken before, so they had to really think about it. And I should say we also gave them a control condition, which was that the system told them what to do, what path choices to make. So we had a kind of GPS-like condition. I'm just going to check on my daughter who's calling out now, and then I'll move to reveal the results from this. One moment. If you wait 1 moment for me.
Okay.
Sorry, I'm in the middle of that talk. Right. Okay. So sorry about that. Most talks I get away with it, but because they're not very well. So here's an axiometric projection of Soho, the region we tested. So you can see some of the buildings now, and you can see a route that people experience in a movie. So they would start the movie in this location near Soho Square, and it would snake its way towards a final destination of let's fill this town with artists, a particular shop. What we plotted here above the space is the route, but each of the colors now represent how many connections the space has. And the first segment of space they start their journey in, there's 6 ways to leave that space. You can go in many different ways out of it. But as the route goes on, there are less options available until they reach the end. And we can look at that by looking at the changes in the degree centrality here. So this route has 2 drops. It goes less, and nothing much happens. And then there's an increase in the amount of degree centrality. And we suspected that based on research, other research, that the brain, if it's representing the space, would likely detect changes in these things rather than just the raw centrality measure. It'd be, as in the brain would be constantly updating what is possible for me to do. As you walk around a city or go through a building, the assumption in the field is your brain is creating possibilities, future options available to you, so that you don't have to stand for ages and think about what it is you might need to do. Humans and other mammals are quite efficient at this, many of them. Not everyone's good at finding their way, of course. But so here's the first key result from that research we published in 2017. We found that exactly as we'd hoped, a key bit of the brain called the hippocampus, where there's a circle in white. So what I'm showing you now in gray is the structure of the brain, and the orange regions are areas where we have a statistically significant effect. So we look at the amount of blood flow, effectively, the amount of change in blood flow that's linked to the activity of the neurons in the brain that are processing the information. And these are higher when the number of options goes up. And these areas drop if there's less to do. If you walk into a dead-end alley, this particular bit of the brain gets less active. So if you walk into 7 dials, there will be a lot of activity in London. There's 6 options to take. But what is all this? There's lots of other areas active in the back of the brain, because this is the eyeball here, and here's the back where our visual system is. What we actually found was that a lot of those other visual areas are also active when you walk into a street and you're using your GPS system. They're not really interested in processing this information generally. It just there's something about the visual information in those particular entry points, in those street entries. So what we're able to do is ask, which is the bit of the human brain that gets more excited when there are more options for you to take when you enter a street, but they're only active when you're having to think about that, not when you just happen to be led by a friend through the streets of, say, London here. And we're able to then pinpoint one particular bit of the brain, and this is the posterior right hippocampus. And curiously, this is the one key bit of the brain that gets larger and larger in London taxi drivers physically when they specialize and learn the knowledge of London, the 25,000 streets they're required to memorize. So you see these structural changes. And here we can see one of the reasons they may be increasing that bit is that if you're having to think hard about finding your way, then this particular bit of the brain is doing that. The next thing we asked with this data is, well, there are lots of different events that happen as you walk along a route. What we just looked at there is the moment you enter into a new street. I see the street ahead of me, I'm aware of what I can do. And that's when we find our really nice effect. There's a particularly key bit of the brain for navigation, interested in options. But we don't find that active when people are making decisions or when they're halfway down the street. It's very selective to the moment they think about where to go. So that's the posterior hippocampus. And we can see here it's really only interested in that degree centrality, the simplest, how many options do I have? When we move forward in the brain, this is again the eyeball of this is the back of the head and the eye at the front. And this is the hippocampus, this gray line here. Towards the front of the hippocampus, in fact, we find this is interested in this closeness centrality. How close to the center of Soho topologically am I? It was also driven by what's the line of sight that I can see, so a little less clear. But what that data suggests is if you were to take Manhattan, Warsaw, or this is Lisbon, you could predict where in those cities would your anterior hippocampus be most active. And we haven't got the data to show this is true, but this is a prediction that we can see, make predictions about architectural layouts of cities and what they would do to your brain in terms of where its activity would be if you're walking around it from this type of analysis. And I'd highlight here, this is something you can get from brain imaging that you can't really get from asking people about. You have to ask every single second, what are you thinking? And you can't do that. It just doesn't work. So we're able to penetrate into how the brain is processing space in this way. We also found that when people did take a detour, so here's an example, they've just taken a detour and they have to rethink what to do. They can't do the original route. What shall I do? And we found that there would be some scenarios where they didn't have to think so much and others where there's a lot more options. And the more options they had to think about in the future, another bit of the brain, the prefrontal cortex, would be really active. And this is the bit of the brain that's critical for planning and decision-making and evaluating the future. So we're quite happy to see that it was really engaged in those particular moments. So I'm going to change tack now. So I just want to share with you some research we did in the past using brain imaging to look at how do we represent measures that architects use to plan out that are currently used. Bloomberg's recent headquarters were analyzed and developed using that same space syntax measure. Now I'm going to turn to another approach we've taken in our research in the last 8 years or so, was to study how people represent space and navigate space on a worldwide level. So the study I've just talked about had 24 people and each one of them cost £700 to require their brain imaging data. So doing even 200 people is ludicrously expensive. It's not something you can afford to do, and it wouldn't add a lot of data extra doing that. But we were very fortunate back in 2016 to be able to partner with Deutsche Telekom, T-Mobile, who wanted to run a big campaign to help with dementia. And the reason they wanted to do that was, or at least the pitch we made to them, was that we currently still lack great diagnostic tools and monitoring tools for Alzheimer's dementia. Because one of the key reasons, I'll go back, this where you can see these points of statistical activity in this map, these are the key bits that get disrupted and damaged in the early stages of Alzheimer's. So it's likely that someone with Alzheimer's, we know from lots of decades of studying patients with Alzheimer's that one of the earliest problems is being lost. So in 2016, we were able to launch an app, which Deutsche Telekom, T-Mobile, funded to try and help us build a tool, a virtual reality on a flat screen test that would allow us to measure how good is anyone in the world at navigating compared to other people. Crucially, this game also tests how good are you at playing video games. Because if we didn't do that, we'd effectively have a test for video games experience and not navigation. So I won't go into the details now, but we have to very carefully equate how good is somebody at video games and then how good are they at navigation. So for example, my mother, who's 70, played this game. There's a video game, I'll show you a movie. Terrible, really not very good at video games, unsurprisingly, but was actually very good at, still controlling this little boat to move around and get to destination. So I'll show you how this worked, but just to say we had 4 million people play our video game thanks to the significant advertising and reach that a large brand can provide. And my collaborator, Michael Hornberger, is the key person who's worked on this with me. And it was his idea really initially. So if you open up and download the game, you can still play it if you get an activation code. And what you will see, I'll just pause this, as you play, this is at level 8. So there's 75 levels in this little video game. And the core idea is it tests people's navigation by showing them a map, like the one shown here, and then they have to try and memorize where they need to go. And this is level 8. So you've had 7 previous levels where it's just a straight line to where you need to get to, and you just see one marker. But here you need to get to 3 checkpoints in a maze of water, driving a little boat, and you'll see that you start in this location. So after looking at the map, you can click in the app, you just tap on the app for mobile phones and Android or Apple devices. You just tap left or right of this little boat in this game called See Your Request, and you get to checkpoints and you win stars for getting to them. And the whole time someone's playing this on their mobile phone, it's logging where are they in this virtual world, recording it, and then sending it off to a server so that we can analyze it. And as I said, 4 million people went in, downloaded this from the App Store or Google Play, played it, uploaded their data into a server, and we've spent the last many years analyzing the data from all these millions of people. So that's, it's a video game, it's all gamified and lots there. So what I'm going to do now is just show you show what the data looks like. I'll tell you why this is important for architecture. We've taken 1,000 young people, 1,000 older people, and they're in different colors. So the younger people are in red and the older in blue. And if I remember, we'll see in a moment. And you'll see them move through a map, a top-down layout. Now they're all simultaneously plotted over. None of them, they're all doing it individually, performing this task. But it's important to say this is less than 0.001% of the data, and it's already quite hard to see all of the. So the red stars here are checkpoints they need to reach. They need to go to these points in the right order, and they all start at the top here. So in blue are the older participants and younger participants in red. So if we watch this out, you can see that already by eye, you can see there's an advantage by age, that being younger makes them faster and more efficient at avoiding mistakes. And indeed, we'll see that in a moment, a large graph. But the data is extremely rich, and I think for decades we'll be looking and playing with this data. And this is just one level. This happens to be level 16, not the one you previously saw. And you can see a lot of mistakes people make, and you can see just how much data. So what I'm going to show you next is all we do is take each of these people for 4 million people and work out how long was the path they took. A really good navigator will do it a very short path, and a bad navigator will take a very long distance. You have a metric of how good each person is. And a lot of the analysis, once we got this developed, we were collaborating with Antoine Coutreau, who is a postdoc who spent years now working with us and is a principal investigator in Lyon in France, working on this. So what can this help tell us? Well, first thing it can do is tell us where the best navigators in the world are. And it turns out in Finland, it seems to have the best navigators in the world. And a lot of the North Americans, Australians, and New Zealanders also are very good at navigating. They're in top group. We also see that older people tend to be worse at navigating, but very curiously, after the age of about 75, people get better and better and better. And this of course, is a selection bias. If you are 95 and playing an action video game on a phone, you're probably a very healthy 95-year-old. And also, people are just more likely to put in random numbers that are higher than lower numbers. And so we're very aware, very precisely able to work out where the bias in our large data is coming from. The other thing you'll see is that there's an advantage for men across the lifespan that doesn't really interact with age. Men at every age point up into this bias point are doing slightly better. So the pink line the red line is males, and the black line is females. And we'll get to why that is in a moment. But the first thing we say is, why do we see this geographic spread around the planet? And the key reason that appears to be is GDP. So the gross domestic product of a country, very strongly predicts how well the performance of the population within that country will do. And we had data from 195 countries in our data set, but only in 75, we had enough 1,000 people to account for male-female age differences. And you can see that Finland does the best in the world, but it doesn't necessarily have the best GDP, which I think is Switzerland. But the higher the GDP, the better the performance, the performance rank. So with GDP comes wealth, access to travel, to healthcare, to education. All these things mean that a population will cognitively perform better in this particular task. And I would add that GDP does not correlate so well with video games experience. You can have a country that are very good at video games, but not so good at navigation. But the interesting thing I mentioned earlier is this gap between men and women. So why are men performing better than women? One clue to this comes from looking at this gap around the world, because in some countries like Finland and Sweden, there is no difference between men and women. But when we look at Lebanon or Iran or Saudi Arabia, there's a much bigger gap between men and women. And indeed, we're able to, in this plot, show that on the y-axis, we're plotting the gap between these two lines. So down here is Finland with a very small, non-existent gap. And at the top is Lebanon with the biggest gap between men and women. On the x-axis across the bottom, we have, I can move this out of the way. We have the rank of how unequal societies are. So on the far left, with Norway and Finland have the most equal society in terms of a measure from the World Economic Health Forum, where women are similarly represented in parliament, have access to healthcare, for travel, can drive, sorts of things in society. Whereas on the far right, we have Iran and Lebanon, Egypt and Saudi Arabia, where the access to all these things is much more restricted for women. And what this shows us is that there is a relationship there, there's an association. So it seems likely, and we can't, this is not a causal evidence, but it seems likely that it's not that women, so it's more likely that growing up in countries where women are not educated at the same level, not able to drive, for example, don't have the same access to education as men, men will tend to have a bigger advantage in navigating the women. So all of this leads to say that we do need more equality in society to improve the population's cognitive skills. We're taking navigation here, but it very likely would relate to other metrics. So I'm mentioning all of this, but the key thing today for thinking about architecture and the environment is this question we ask people in our video game. Did you grow up in a rural setting or in a city or somewhere between? So what I'm going to show now is a plot. On the y-axis is how good the performance is. So high score now, it's not the error, but the higher the score here, the better the performance. We're going to show across the age lifespan up to the point where we have this selection bias. We're removing this data now, where we can, in this section, we can be confident. Now, we already know that this will decline with age. We get worse as we navigate with age. And we know that men have this advantage on average. But we're going to plot now in green are people who grew up in these rural settings or outside cities, and in gray, people who grew up inside cities. And what we found, to our surprise, was quite a strong effect, a negative effect of growing up inside a city. And by growing up inside a city, I mean people who grew up in the sort of downtown, they lived in the city, not on the suburbs. And so what you can see, but by big effect, what I mean here is that a woman who reports growing up in a rural setting outside a city in her 70s is as accurate at navigating as a woman who grew up in cities age 60. So there's a 10-year gap in cognitive loss if you've grown up in a city as a woman. So that's not a small effect for me. That's quite a shockingly large. It's smaller for men and it's smaller earlier in the lifespan, but it's there and it gets bigger as we age. But we noticed that this effect, this is the average worldwide effect. On average across the world, growing up in cities is not so good for your navigation skill. But we noticed that it was particularly driven by some countries where there were much bigger effects than others. We also noticed at this time that Jeff Boeing, who's a geographer, had found a way to calculate a metric about how disorganized the layout of a city was. So Chicago is a very organized city grid layout, whereas Prague is much more disorganized. And he could measure this by just plotting here what's all the orientation of the different streets. Chicago is pretty much just two directions, east, west, north, south, whereas Prague has many different directions. And here you can see many different countries, cities plotted out, where down here, the one that stands out to me is Sao Paulo. It's completely disorganized. Whereas up here, we have Chicago and Toronto, if I remember right, is the most gritty in the world. So what that allowed us to do with that metric was to say, well, why maybe one of the reasons some countries have a worse impact of the structure of their cities on navigation, maybe because of this. But if you grow up in a gritty city, it may not be helpful for your navigation skill. If that's true, we should find that here on this graph, the larger, the more negatives, they're going left to right, over in this right side of this graph, the worse it is growing up in cities. And on this y-axis, how organized how disorganized are the streets. So what we found in our graph was quite a strong correlation again between how gritty the city streets are. So these are the lower the score here, the more gritty they are. and the larger the effect size of growing up in a city on navigation skill. So that does support the idea, and this is, we ask people, where did you grow up in your childhood? So it supports the idea that growing up in a city of a country that has very gritty cities is not so on average beneficial for navigation skill as growing up outside the city, or in a city like Ireland, for example, has the most wiggly streets in the world. And there's no real, it's a very minor effect in Ireland. Romania, it's almost better to grow up inside cities. When you look at Romanian city layouts, they are like spiders' webs. They can be very complicated. So this makes some sense to me. So, but I'll just play a short video. We also thought about this a bit further, thinking, well, here are the layout of two of the levels in our video game, level 27 and level 58. On the right, if you focus on that right-hand video, it's a very gritty environment. There's just left and right turns. And if you look at the left-hand video, it's much more curvaceous. It's got lots of twisting turns. There's almost no straight lines in level 27. So what that allows us to do is ask, if cities are not helping your navigation skill, are people who grew up in gritty cities more sensitive to the level on the left, level 27, than they are to level 50, I forget which one this is on the right, 58. And so here's an example analysis of two of the levels in our game. And that's exactly what we found. So what we found is that we take participants who grew up in countries where there are very gritty cities, and we find that those people who grew up in gritty cities are really bad at navigating our most, like that level 27 you saw. They would find that very difficult on average compared to the more gritty ones. And in fact, what this graph shows, so this is the effect size of how negative cities affect navigation performance up and down here. So there's a big effect. So what this graph at the end here is saying, if you take a very curvaceous winding level and test someone who grew up in Manhattan, they will be bad at that. That's what that says. Whereas if you take someone from Prague, who grew up in the city of Prague, they'd be less bad at that level than someone from Manhattan. But over on the other side, it suggests flip that round. If you grew up in Manhattan, you might actually be better at navigating some of these gritty layouts than someone who grew up in Prague. And it's not just Prague versus Manhattan. It's lots of different countries here. So it's not just one city. What does this tell us? It tells us that growing up in grid-like layouts is not simply bad for you. What it does, it adapts you to being more efficient at navigating in grids and less efficient at navigating more windy, complex environments. So what that says is, on average, because the world doesn't tend to be gritty, you'll have a better time if you grow up outside a city or get some exposure to non-gritty environments. But effectively, our childhood experience of the architecture in cities and their layout, this evidence does suggest it plays a role, and we were able to publish that in Nature, and we're very fortunate to be on the front cover, get a lot of coverage for this, because it's the first evidence, as far as we're aware of how the layout of the environment in childhood affects later skill development. So I'm going to wrap up with two further steps. I started my talk by talking about degree centrality, closeness centrality, space syntax approaches to city analysis. What we did with our video game, because we had 45 levels where people had to do that task I showed you, we took all the ways in which people over the decades have developed measures in space syntax to analyze those layouts. Here's one of our level examples. Here's one of our levels with 3 checkpoints. And we can analyze the lines. We can take up the segment integration, this degree centrality, the closeness centrality, betweenness centrality. We can look at the entropy of a given level. And what we did in a recent paper that just came out in July, it's coming out in July, it looks like to me, not in the future yet. But this paper is out in Cognition. You can find it online, where we looked at 10,000 people who had played our video game all the way to the end in detail, and then looked at across these levels, what were the features within those levels that made them good or bad for navigating. So we're interested in which of the levels were extremely difficult to navigate or very easy, and why. And because there are 58 metrics you can use in space syntax, we used a method known as lasso to downgrade, like to make these different metrics compete against each other to explain the variance in the data. And this is the key plot from our article, which, as I say, has just come out, is on the y-axis is the impact, is the effect size in our model of different parameters. Many of the metrics in space syntax, like intelligibility is a key one, did not predict levels being bad. But our metric we used in the previous study of the network, the entropy of the streets, this metric here, how disorganized is the layout, was one of the strongest. Unsurprisingly, we find that if you have lots of destinations to memorize, people do worse. And if there's fog, people find that harder. These were not a surprise. But it was finding the size of the area, also unsurprisingly. If you had a big environment, it's harder to navigate. But what stood out as unusual were the number of circles, which also makes sense. But finally, the segment integration. So this is, for each bit of space you're navigating through, how integrated is it to the global network? So environments that had good, clear integration, people found easier to navigate. So in this article, we've written up, and describe what this implies for the design of buildings and layouts. That this, to us, is the largest number of environments co-analyzed with the same participants. We've got 10,000 people, which we've looked at in detail. Okay. And what I hope to look at now is what I hope will be the most interesting to all of you, which is to really delve into the architectural experience. So far, I've been really interested in how does our brain map space, what happens when we navigate around a city, what makes an environment easy or hard to navigate, etc. In this last piece of work, I'm going to talk about research by my PhD student, Lara Gregorians, who's just wrapping up her thesis now on this, where we set out to do a brain imaging study, much like the one I talked at the beginning about. Rather than having people navigate through a city street network that they'd learned, we wanted to expose people in our brain scanner to lots of different types of architecture, lots of experiences, and really vary two key parameters: how complicated were the spaces to take in, the complexity, and also how negative or positive were they. In all my research today, I've really focused on that mapping question of how do we represent the structure of a city or a building, but not so much on the effective, the aesthetic value of a space. And so with this new study, I was really excited to step out of the comfort zone and ask that question. What does the brain do when you're in a beautiful place? And really, ideally, we would like to do mobile brain imaging to get people into really immersive, real spaces. Put people in a cathedral, put people in a wonderful luxury holiday place. But that's still a big challenge. We can't easily do that. With what we did here is to have participants watch first-person view movies of building tours. And we spent 6 months collating an archive of really effective movies we thought would capture pleasant or unpleasant experiences that varied in how spatially complex the environments were. What we published last year was a report in the Journal of Environmental Psychology that Lara is the first author, where we wanted to ask a number of questions using these movies. We had about 78 participants watch their way through a set of curated movies. These are about 40 seconds long, and that length of time is optimized to be able to do our brain imaging analysis. The first question was built from Anyan Chatterjee's team at Pennsylvania University. Is the valence, how positive or negative you experience the space, or in particular, how positive a space is it correlated with fascination, coherence, and hominess? So these are three construct questions you can ask someone about a space. And they argued previously that if a place is seen as positive, people like it, they also tend to be fascinating, more likely to be coherent, and are more likely to be homey and can have that homely feeling to them. What wasn't previously looked at is arousal. So you can feel you like a place, you find it nice, but you might find it relaxing and pleasant to be in. Or you might like a place because it's really exciting and really drives your adrenaline up. These are very different positive experiences. Similarly, for negative experiences, you might find somewhere really depressing that lowers your mood and makes you feel really like doing nothing. Or you might enter into a place that is, say, terrifying or really unpleasant and really arouses you. So you can have this real dichotomy between these two properties. But is arousal related to fascination, coherence, and hominess? It's unclear. We suspected it might not be, but we wanted to find out. Finally, related to that mapping I've talked about so far, do these aesthetic and affective dimensions correlate with complexity and the unusualness of a space? So if places are more spatially complex, are they more fascinating? Are they generally more positive? Do people think places that are untypical in our movie set, places that are more are seen as more positive, they tend to be more complex or more unusual? And finally, how is that the extent to which someone likes and says they find a place, they like it, related to beauty, like general aesthetic? Do you think this is beautiful? Are these things separable, or are they quite related? So here is a movie sequence that people would see. I'm just schematically, Lara's laying it out. You see in the paper of one of our example positive movies of walking around a beach resort in the Maldives, I think it is. And it's a really expensive holiday home, really rich, features, and the architecture is laid out for a beautiful sea view. And they watch the movie. They make ratings about their arousal and their positive, negative experience, unpleasant, pleasant. And then we would ask them to rate how complicated it was spatially, how unusual it was. We also should say before they did this, they were given a guide for what are examples of a spatially complex or a spatially uncomplex or positive and negative. So for example, in our stimuli, we had a games arcade with an enormous amount of flashing machines everywhere. It's extremely visually stimulating, but it's only a single room with a door out of it. So we explain to people this is spatially really simple. It just looks visually complicated. So we, in our movie, separated out visual complexity from spatial complexity. I'm just going to show you one of our movies. So this is one of our movies for our negative category, which is Preston Bus Terminal in England. So if you ever had the misfortune to be there, here's an example. So we looked at lots of possible places, but the example here is like it's classic brutalist architecture. It's may well have been excitingly designed by the architect, but it's now been added with very neon pink bins. There's a lot of signage that isn't well set out. It's quite darkly lit. It's not somewhere we expected people, and it was indeed rated as quite an unpleasant place. So people lying in the scanner watching a movie like this, not all the movies are so jerky. This just happens to be quite a jerky movie. You got a sense of the length of that movie, the exposure people would have, and we would look at their brain activity. So we'll come on to the brain imaging in a moment. So here are some of the movie frames, key frames from some of the movies we found when we went through. So the Maldives hotel room I mentioned was the most highly positively rated location. An abandoned, decrepit mansion we picked out came out as the lowest, most negative environment we picked. We found the games arcade was the most arousing, as I mentioned. There's lots of flashing lights, and the people found the library the least arousing. The Royal Palace of Caserta, so we asked people had they been there before. People hadn't, so we were able to analyze that. Was the most spatially complex. There's lots of doorways. An infrastructure tunnel where you just go down a tunnel, unsurprisingly, was the most spatially boring. Fascination related to an underwater hotel we found, and the most unfascinating was a stairwell in a UK tower block in a block of flats. Coherence related to a large open plan kitchen, like a new build house, and someone's like hoarder location, this little room you open up full of bric-a-brac, like disused items, was the most incoherent. And finally, we had like a lovely French chateau with really homey feel to it, whereas a graffiti military base, unsurprisingly, was the least. The least homey environment. I'm just trying to move this. There we are. And unusualness, again, the underwater hotel was deemed a very unusual location, and a supermarket the most boring. So I'm just showing you this to give you a sense of what the material was, the stimuli we used to kind of drive people's, and this is really important to be aware. It's quite possible to have redone this experiment, pick very different stimuli with different properties, and you might well find very different results. But we very carefully worked as a team through to try and pick what we thought would be representative spaces that would fit our criteria. We're very happy for other people to find other results and tell us different stories, but this is what we opted to do for this study. So here on the left, so there's a lot of data here. On the left, I'm just showing you the entire layout of 78. I think each of these dots is a movie, and it's the average rating across our participants. And so what we can see here are, for example, what we had predicted from our data was that if we look at this top column, if somewhere is deemed highly positive, it's more likely to be fascinating, it's more likely to be coherent, and it's more likely to be homey. So they're quite strongly correlated. These are these dots showing you that these lines go up. If one goes up, the other one tends to go up too. But that's not true of the complexity, the arousal, or the unusualness. So what that means is you can find them just like really negative or really positive, and you can't tell whether it will be complex, unusual, or arousing. They're just not related. So taking across all these different correlations, on the right-hand side, you can see a kind of connection plot of what the strength of these associations is. So that coherence, hominess, and fascination all relate to valence. And this replicates a previous study by Coburn from Anjan Chatterjee's lab, where they found exactly that, just using photographs. So we now have evidence this does replicate. And what we can see here is that arousal just doesn't relate to that network. But fascination is linked to all of these properties. So somewhere that's fascinating will tend to also be homey, coherent, and be more positive. In this data set, we found that more complex places tended to be more fascinating. They tended to be more unusual, and they tended to generate more arousal. So go read the paper if you're interested to learn more about what we found in that data set for understanding the experience of architecture using movies. And again, I fully admit this is a challenge of using movies but it builds on work that was just using pure photographs. So we're moving our way forward, hopefully, to exposing people to actual first-person experience. So where we are now, and this I put these slides together today because we only got the data in recently, was to scan 28 people in our MRI scanner, watching those movies and rating them for valence and complexity. And what we found in our first set of slides, so what I'm showing you is, I'm going to start with the complexity. So I'll start at the top by just highlighting again, here's our infrastructure tunnel, the least spatially complex environment rated by our participants, and the Royal Palace of Caserta, the most complex environment. So what we've done over our set of movies, of 48 movies in our MRI scanner, half of them are 24 of them are unpleasant, are simple, and the other 24 are highly complex. And what we've done here, if we start on the right-hand side, is to see which bits of the brain are more active in those simple movies. And what we see, and what I'm showing you now, is let me just move my out of the way. So what we're seeing here at the top is a glass brain. So this is all the activity shown through the brain. And unless you're an anatomist or are used to looking at brain imaging, it's tricky to understand what all that is. But I'll focus you at the bottom, which in gray is the brain structure of the average of the participants. And in yellow shows areas of the brain where there's more activity for simple environments. And the answer is really boring. So for very simple environments, the primary visual cortex at the back of your head is more active when you're looking at these kind of simple tunnel-like spaces, but not much else. If we go to the complex environments, we actually see the entire network of brain areas associated with spatial navigation, all coactive. So when I'm just passively viewing, watching my way around Caserta Palace, if I haven't been there before, we see the hippocampus, that bit we talked about before. We see a whole lot of other structures that are shown in this image here that I won't go through. But they're all critically, if you damage anywhere in this network, you will end up being disoriented in space. And indeed, these are the areas that are early affected in Alzheimer's. So what that shows is unsurprisingly in some ways, that the complexity of a space as you observe it drives the navigation circuits of the brain. So that was not too surprising to me. What I've really been looking at with this study then is, what about valence? What actually happens when you experience a negative or a positive space as you go through it? So we might expect brain areas that are related to kind of disgust, you don't like things, to be active when you're in the negative, or maybe the beauty areas of the brain to be active in places that are positive. So what did we see? So I'll remind you, and again, at the top, the images on the left is an image from the Maldives Hotel. This is one of the most highly rated movies in our set for positivity, and an abandoned, decrepit mansion on the right. So again, what we're doing here is taking 24 movies where they're really negative, comparing them to movies when they're very positive, and taking the brain activity and contrasting them. So on the left-hand side, these are the brain areas that are more active in the human brain when you're viewing positively valenced movies, places you tend to like. And what we were a bit surprised to see is that most of the visual pathways of the brain are more active when you're viewing these movies. We weren't sure what we would exactly see here, but we see all the way through to these spatial brain areas more active in our positive movies. We know this is not driven by the complexity. It's orthogonal to it. So we know it's definitively not just that our positive movies are more complex. As we showed you in the previous analysis, there's something about positive movies that tend to drive our visual system. And this is just step one of our story here, really, because it strikes me that there's many, many features if you just look at these top two images, the Maldives and the decrepit mansion, you can see there's probably more curvature in the Maldives Hotel, more light, more transitions, all sorts of things are happening in more positive spaces that drive the brain areas that we're seeing here. And I think for me, the most exciting bit when as a neuroscientist looking at a map like this is actually this bit in gray towards the front of the head. Here's the back of the head and the front. There's a bit of the brain, we can just see a small amount active there. This is not part of the visual system. It's not being driven by the lighter levels in positive movies. This is a brain area that tells you about the value of things. So if you show people lots of different objects and say, just look through and decide, is this man-made or art or natural, go through these. High value items will drive more activity here. So what we're seeing here is, and we didn't see that if I go back to the previous slide, there's no engagement of the frontal cortex, the sort of more high order part of the brain for complexity. But when it comes to value and you're looking at beautiful places, you tend to activate that value area. We are very surprised by what we saw for the negative. So for these places people dislike, we see brain areas that fulfill a certain circuit of the brain, and we're still trying to unravel what this is. We've been asking experts what they think might be going on, and somebody highlighted that actually the overlap, a lot of these areas overlap with areas that are linked to depression. Mm-hmm. And that's not so surprising that that decrepit mansion, a stairwell in a disused council house, broken down set of flats where everything's gone disgusting, or that Preston bus terminal. For me, it's a negative space. I'm not an architect. I have colleagues who will say, I love brutalist architecture. For me, that's exciting. But for most people we scanned, we excluded architects from our set. That's not. So we're still trying to figure out what these are. But what we will be doing over the next year is going into our movies and working out what are the features that drive different bits of it. Because if we just stop there, that's not really enough. We need to know why is so much of the visual system active in these particular movies. And at the end of it, we hope to get more into an understanding of the aesthetics of how the brain reacts to the aesthetic features of space, not just the spatial mapping. Okay, I just thank the funders who supported this research, particularly with mapping and with our video game. And I've got more things I could talk about, but I'll stop there to open a discussion if that's good.
Yes, okay. That's really, thank you. So thank you so much for this really rich presentation. So many different ideas and also so much data also to correlate all these ideas. And I was looking at the presentation and thinking, okay, where do I start our discussion? So I will just pick up the threads. as they come over. So I found it particularly fascinating that you showed us this example of how a video game can be used as a very effective tool to, first of all, collect a large amount of data involving so many participants and also so efficiently, but also to test this aspect of navigation. So congratulations, a really wonderful example of how we can use the digital also to test hypotheses of things that happen in the non-digital world. I also found particularly interesting the kind of correlations that you presented to us, specifically with the gender issue. As a woman, naturally, of course, I am particularly sensitive to it, and I have to confirm also from my own experience that I happen to be married to a German Bavarian who grew up in the forest. And I'm always very jealous of my husband's exceptional navigation skills. I always say, I'm walking in the forest with you and you're basically an elf. Because I know we can, sometimes I get very nervous that we go into these dark corners and we always figure it out. So I can really attest to that. But I can also say from the other way around, that navigating a city, I'm the one who usually figures things out better. So we do, but it's interesting how we can really see definitely the correlations. What I wanted to ask in particular, also in connection with the topic of neuroplasticity, have you integrated in your research any methods to understand is it possible to develop further navigation skills, for example, through life, or is it really deterministic? Because you mentioned that the kind of childhood background and the spaces that we somehow got wired to navigate easier, is this deterministic, or in how far can we, over the course of a lifetime, change that or improve such skills?
Oh, that's a great question. I think that's a really good question, and one actually I don't think we still lack a lot of knowledge about that. I'm surprised in 2023 we don't know more about the answer to your question, because it's a very good one. There's also this is sort of trivial way of looking at it, where you can kind of, well, I don't know if trivial is the right word, but we have done some work trying to look at can you help people to learn a new city area faster? Like, what is it you can do based on guides to navigation skill? Like if your husband, who's Bavarian, would say, right, you should do this is how I solve it. We tried that and it didn't work in our case. But your bigger question is the kind of, are we genetically programmed with a certain ability to navigate, and to what extent can you moderate that? And that's hard to say. I think there's some work showing there's quite a strong genetic component to our ability to navigate. You're kind of born with a level of skill, much like many other factors. But our work and others really, with this work we published in Nature, strongly indicates that your upbringing does impact your skill. The extent to which it does over the genetic background is still hard to say. Like to quantify it and say, oh, it has this much effect. But overall, the data does suggest, exactly like you said, it is worth exposing children to different environments and different skills. Both the work where we've looked at cities, but also the gender inequality. The countries like Saudi Arabia, where women are not allowed to drive, there is a gap in their spatial skill that is very evident. And does suggest that more should be done to really get people active. I also get related to that. It's like, are you more likely to get Alzheimer's disease if you're not good at spatial, or you don't practice spatial navigation? And we really don't know the answer to that either. If there is an effect, it's probably not massive. The big effect for Alzheimer's is keeping healthy and being active is the most important thing, and keeping social networks alive and engaging over probably navigating. But I think it's a good empowering thing to be able to navigate and not be scared going in new places, because you never know where you might end up in life, and not taking risks and going places is limiting your life experience. So I think for those reasons it is worth doing. So hopefully that's a useful answer to your question, but it's a good one.
Yes, well, it does bring me into other questions, because I was also thinking about the role of curiosity in all of this, and also curiosity not just as a motor for exploration, and not just in childhood, but also this kind of idea of lifelong learning, and also how perhaps we can think of how we could design cities that encourage curiosity, specifically in the elderly, so that they feel perhaps less anxious about going out, and that we can somehow modulate the environment we already have. I mean, we know that we cannot rebuild all cities from scratch. We cannot rebuild great cities into complex cities so quickly, but perhaps try to understand what are the components of more complex cities like Prague or Lisboa or London, and try to integrate these components. And but then we also have to deal, for example, with motoric issues, because, for example, in the case of the elderly, we can offer them complexity, but if their body is not able to correspond, then we also need to adjust that. So my next question has to do in connection with this topic of curiosity. Now, more later in your presentation, you showed this very interesting experiment with different films, and more related to the experience of architectural space. Did you do any experimentation trying to understand what's happening in the brain when we watch, for example, horror films? Because I would be curious to know how, because somehow we know that it's a simulation, we know that that's not a real space, but we know that somehow humans also enjoy looking into those horrible things, or derelict environments and so on, and can find them even somehow cool. So how could we explain this?
Yeah, that people I don't know that anybody's actually done what we've done here of taking a horror movie and then looking at the activity as you go through it. I know there have been interesting studies looking at horror movies in terms of other properties, but off the top of my head, I can't think of a study that's gone through a horror movie and kind of analyzed the brain activity. We've certainly not done that. But you're absolutely right. There's a kind of sense of lots of things happening there as people's heart rate goes up, and all sorts of things happening in a horror movie that are fascinating. I wouldn't be surprised if somebody's doing it or analyzing it now. So yeah, we don't know a lot about that. I think the nearest in ours is that when you raise that question of curiosity and that kind of absorption, there are movies we have that are just really boring. You're going down a tunnel and there's not. Curiously, people do remember those. They stand out later. So it's not, we found that the memory, and they come out of the brain imaging scanner, it's not the kind of like the Royal Palace of Caserta they remember, or the underwater hotel even. It's strangely these sort of tunnels. So they really stand out. But the curiosity, what we'd love to do is go back to those movies and try and get kind of people to rate for them when they're most likely to feel curious. And when does your curiosity peak? So going through a tunnel, nothing's happening. But as you get to the exit and you think, what's going to happen? And then you're there. I think there is an element of that would seem to be a key event. But it's confounded with the change of brightness and all sorts of things. So we need to be able to be very careful in our movies to see what we can do. But I'm hoping we will be able to get to some of those. And curiosity really is a key one. I think it's, we'll have to see. We aren't there yet.
I also have another question, and then I will give the word to our students, because I'm sure they would have many questions. If you have done or have considered any experiments to try to see the effects in the brain of overstimulating environments. So, for example, we know that, and you did show this video with the video game arcade, which probably gave a lot of idea of this kind of simulation. But we know that specifically in cities, Asian cities in particular, there is a lot of information in the environment, and people more and more feel the negative effects. Did you do any experiments in this regard?
No, it's a great question. No, we haven't. And we could, to some extent, look at the extent to which these different movies are, because we have the arousal rating, we can go and look at that. We haven't analyzed the data with respect to arousal. I should say as well, because of time, I didn't go into the details, but we also do have movies that we systematically varied how much green space and blue space there was, and how many people or not people there were in the movies, because these are key factors that drive brain activity. If we just had lots of people in our negative movies, you'd see a lot more areas of the brain to do with looking and processing people, and we were very careful to control for that. What I don't know yet is how the brain reacts to the green space. I was also very careful to have negative and positive green space, because I didn't want just green space to be driving, just the greenness of it. So I'm hoping we'll also with the data be able to see what is it about positive green space that goes up in the brain. Is there anything different about that? Does that make sense?
Yes.
What is an environment that's inspiring and green or blue over a green? So we have, for example, one of our movies is an old UK public school. It's not very nice, a lot of graffiti and concrete. It's dismal, but it has a lot of green space. You're in a field, you're surrounded by green, but it's just really not very nice. Surrounded on edges by concrete. So that is the kind of attempt we had to kind of look at these things. But yeah, your point about how we can be overstimulated is a really good one. So there was an interesting study half a year ago now, time flies by, where they took people along a major urban motorway for an hour, made them walk along it, walk through a natural and lovely forest, and then they scanned people afterwards, responding to faces, and they could see substantial differences in the brains of people who'd experienced an awful motorway or a forest walk, on how their brain reacted to emotional stimuli of emotional faces. And it got a lot of press, a lot of coverage, because it feeds to your question about how does the environment affect us. So I thought it was a really interesting study. It's not a perfect study, I should say. There are problems with it too, but we haven't done anything like that. It's a really interesting question.
Well, you could find it interesting to look at in our channel, because our last conversation was with Anne Sussman. She wrote this book, Cognitive Architectures, and she presented us her research with eye tracking, and also how eye tracking can also actually also be used as a very effective manipulative tool to encourage people to consume more. And I had to think about it now, because you mentioned with the positive responses we have, for example, to smiling faces and so on. And in quite detail, she explained also how this can be used. But this would be maybe better for further conversation. So I would like to ask our students here in the physical classroom to come over. We have a meeting owl, which is our medium for questions. Yeah. We just need a little time.
Sure.
So the questions going in the same direction like the one before we had. It's about how cities should be created or developed, because you managed that maybe if there's less brain action, you can lose your skills. But in the other way, if there's too much stimulation, we could get sick of that. So what is the right answer to this?
Yeah, it's a good question. I think it's a really good one. And the obvious answer is partly we use cities and buildings for different things. So the context matters a lot, doesn't it? So if there's part of a building, like in the meeting room you're in now, if you had to work all together in that one meeting room all the time and everything happened in that one room, it wouldn't be as effective. I'm guessing you have other spaces you might go to think or work in rather than meet. So our cities need to provide the support for all the key things human needs, We need safety, we need comfort, we need food, we need all the sort of basic things, but we also need that stimulation, but we don't need overstimulation. And I think that's exactly where the research can go, is to kind of fill us in on how does that affect us. There's a lot to be done there. And people have been working on these topics for decades. This is not a new line of research to understand what's beneficial in the environment. But diving into what I talked about today, it does suggest there's a benefit to not building grids. Even though you might find it easier to navigate them, they're not actually good for developing navigation skill. But that's for the development on a city level. But if you build it so complex in like Sao Paulo, it's going to challenge a lot of people and cause more stress. So we don't currently have data to say this is the way to do it, and it would be nice to get it. So it's something that needs more data, I think, and more thinking. But it's hard data to get, I think, is the challenge in this area.
Yeah, but maybe it's good to have, in general, a mix that you have those differences concerning different contexts.
Absolutely. Thanks.
Thank you. Next question. They are a little shy today. Is there a question coming?
Yeah, should I ask from here?
No, it's better if you come over. We have, well, actually, I would say that our building here is quite an example of post-brutalist approach. As you can see, it's quite industrial and monochromatic, and I think that sometimes it doesn't encourage very energetic moods. So,
Okay, so I wanted to ask that, do you know, like when you were a child and you came home with your parents in the car and you were sleeping, like right before the last turn or something, you woke up without nothing. Like, I don't know if it happened to you, but I've heard that many people do this. And I think that it has to, like, again, with memory of architectural space. And I was wondering if you studied that, or if somebody studied that.
The moment of waking up from after a journey in a car, or
I mean, not just waking up, the fact that you wake up every time in the exact same spot, like right between the turn or right in the same area, like you recognize that you're getting home.
you know that you're
Yeah,
getting there, you wake up just
in your
before.
sleep, yeah.
Yeah, it's a great question. No, I've been wondering about that for years, but as far as I know, nobody's actually got to that kind of how is it that our brain does that of shifting us. I think there's some interesting research in bats, for example, where they have to fly en route, then change what they're doing, and you can see all sorts of changes in the brain as they have to do that. But the key thing you're interested there in, I think, is the switch between kind of automatic, autopilot, not really thinking, you're almost asleep, to then suddenly, I need to do something different, and how the brain orchestrates that future timing and the stimuli coming into there's a lot of different brain circuits involved, but very likely there's a particular structure in the brain involved, they call the striatum, the nucleus accumbens, and there's sort of a brain area there that's involved in habits and processing habits in relation to goals, and like ordering your actions in relation to things you learned, that likely underlies that type of processing. And the stuff I've been talking about today is all the stuff where you're using a map, like how are you thinking about the space, or you're learning a new space. You don't have a map, like people walking around our movies and viewing Caserta Palace, they're going through corridors and taking it all in. And our assumption is that naturally your brain maps space, it learns spaces. But that experience of kind of driving home and you just at the last minute, oh, wait, I need to know, is very different. It's a familiar environment. So yeah, we do need to know more about it, but we don't. It's a good question.
I was thinking, like, if you could use the same, like, sensors that activate you, like, maybe to help the elders, like, organize themselves, like, the same, like, repeating, and then automatically manage to do it. Like,
yeah,
maybe even elders with dementia or something would be able to develop like this.
Yeah, I think there are steps made to use different devices and approaches to help people with dementia to learn like habits and routines for doing things, because it's very hard to have that flexibility, just like you said. Yeah, absolutely. Yeah. I mean, something I've been mulling over in the last, thanks for the question, but mulling over in the last months is the extent to which video games are billion-dollar industries now, and they have to make environments that are intuitive to be explored and people curious about things in them. And if we had environments in the real world that were built to the same quality, that helped really engage our curiosity and just naturally led us to what we needed, it would be amazing. But that transfer hasn't really happened. And I think most video games are designed for a very particular purpose, combat or something. There's conflict in most of them. You have to whack and kill things often. Anyway, there's another question.
Yes, well, before Milton's question, I would just say that I did play quite a lot of video games growing up. And I think that I remember very often this Treasure of the Monkey Island. You all know about it. And I am sure that playing these video games somehow already programmed something in my mind of, you know, traveling, living in another country, negotiating, having, meeting different people, being a little adventurous. And I really think video games have a lot of good qualities to give also.
That's great.
Milton, you want to make a question also, please go ahead. We can't hear you, Milton, you're muted.
Well, first of all, I just want to say, you may be a non-architect, but this is the best talk on architecture I think I've ever heard.
Oh, thank you.
The most informative and helpful for my own thinking. So I just wanted to ask you to touch on two things. One of them was whether the GDP correlation has to do with people who own cars as one connection, because it seems to me that what you imprint in your mind about navigation may relate to the stress related to the speed of having to make decisions, right?
Yep.
You know, if I can just walking around, I think I don't need to have a lot of attention to it, which brings me to the question of this triatom and habitual, you know, or unconscious navigation. Seems to me that what you remember consciously must happen when you displace other things that have your attention. So this triatom's helping you walk around, and then something arrests your attention, or you need it when you're crossing a street, or there's, you know, danger or noise or something that is attention getting, how that fits into your thinking. And the last is, I'm just starting to read about the insula, know very little about it, wonder if there's a connection there.
Yeah, let me start with the end bit, where in a recent study we just ran, I was expecting the insula might be more active in these disgusting spaces we've used movies, and we didn't see it at all. And I think it might need us to go in and pick out the particular salient movie frames where it is literally more disgusting in some movies. They're not just unpleasant, but they have that quality of like things are decaying, or we'll see. But I don't know. But that's just very specific to the insula's role in kind of disgust and that body kind of. But we haven't really, you know, there's more going on in the insula than that. But we didn't see it so far in much of the work. I'm surprised. We have seen it in other things, but not here. So we'll have to dive deeper on that one. Your second question was about the striatum and that kind of how the intention, the environment might drive things. I think that's a fantastic perspective, where we've tried in a number of articles over the years to think about wayfinding and a navigation process, because a lot of what I looked at today was really wayfinding. You're given a map, or you've been somewhere yesterday and you need to go back using your memory, and how you find your way. And indeed, in that scenario, if you're just constantly thinking about the map the whole time, you're actually at danger of not taking in risks, and you will use up more glucose in your brain to do that. So it's not efficient. So we do need to switch in and out of these modes, you know, regularly. And I think we don't know enough about that. Again, a lot of these questions highlight we don't know really the detail there. And I think, you know, one of the things I talked about today was this tracking of the structure of the space. What are the connections that exist for me? Was only there at the moment you enter into a new space. It's not constantly being processed. It seems to be that there's processing activity at the moment. It's important. So I think that fits with that idea that you are processing things efficiently. If you're an optimal human, like most of us, you're able to do that. But we don't know. I don't think we know enough. But your first question was really interesting. I've forgotten what it was. Can you remind me what you started with? It was around.
Yeah, it was whether or not you record memory of places that have navigational significance when you're stressed. So, for example, driving fast.
Oh, yes. Yes, that's right. You were asking, is the GDP related to car use, and then this link to stress and driving and it being beneficial? Absolutely. In that GDP correlation, car ownership is related to the score. In our original paper, we showed that the countries with higher car ownership tend to navigate better, but that's correlated with GDP. What didn't fit with that data was Scandinavia. So Norway, Finland, and Sweden don't have as many cars, but yet they're better than everyone else. What we looked at there was the fact that in their school system, children are taught how to do orienteering. So
Yeah.
they take a map and run around in a field and compete in their ability to navigate with a map. So we think this in the paper, we argue, might explain this odd phenomenon. But most recently, we did a study. We asked 1,000 US citizens as part of a follow-up study for our Nature paper, at what age did you learn to drive independently? And people were worse at navigating if they learned over the age of 18 to drive. If you learn to drive earlier, you will tend to navigate more efficiently. So that does answer, I think, we've not published that yet, but it exactly answers, I think, your question that if you're learning to drive as a skill, it will enhance your navigation. But we found the number of hours people drive per week doesn't matter. So this again goes back to the kind of, it's what you did in your childhood or development that sets you out on a course. Growing up in Bavaria or in the mountains and forests sets you up for good skill. But yeah, there's other work on the stress. So I think that link between driving and stress is a good point about the speed at which you're having to make decisions. And if you're not used to that, it will make that difficult, particularly in the game we build. So yeah, there's a lot to figure out there. People have shown recently that you'll take less shortcuts if you're stressed. You'll be less efficient at solving problems in navigation. Not too surprising, but they've kind of been able to pin that down. But yeah, we've not done too much with stress. But it's very interesting. So there's a lot of good questions there. Thank you very much, Milton, for asking all those.
Thank you, Hugo. This was terrific.
I would make also now a following question, because it was already before, and now with Milton's question, I also thought about it again. If you have compared navigation skills between car drivers or people who are mostly car drivers and pedestrians, because also navigating and doing decisions of navigating by foot, specifically when you're in a city, it's also, I would say, different skill set. So did you do any comparison?
No, it's a great question. We haven't done that. I can imagine running quite a nice study where you've optimized the task to be good for car drivers or good for people who do more outdoor walking or pedestrian rural navigation, and see whether they're, you find the effects you're looking for. I still think a lot of this is quite mild. Like even when we do find these effects, like the benefit of learning to drive earlier, it's beneficial, but it's not a huge effect. By far, the biggest one we see is age. As we get older, we get less good on average at navigating, and the gender effect's surprisingly big. But there's an advantage of education. If all of you who've done more education in this call, you have an advantage over people that never got formal education. So we see all these things increment. They kind of all boost your navigation skill, but it's to some extent genetically set.
So here in the classroom, any more questions? Maybe one final question? No? Okay. I don't know if in the audience there would be maybe room for just one more short question, and then we would finish. No, it doesn't look like that. So I would just make one final comment, and not to extend also our session too much. If you have looked, because you did mention that you didn't include architects in one of your experiments, exactly because you wanted to avoid the brutalismus bias, so to say.
Yep.
So, and here I would definitely agree, also as an architect myself, that our education and our appreciation of aesthetics has a different range and also different focus than most people. And also in connection with the conversation we had, the last conversation with Anne Sussman, she did brought up some problematic aspects of modernist architecture. And she actually brought the hypothesis that perhaps the fact that Le Corbusier was in the autism spectrum and Gropius might have had post-traumatic stress disorder because he was involved in the war, that might have been factors that made them create environments which are so regular, that need absolute order and clarity and so on. So I wanted to ask you, did you do or consider doing any studies that take in consideration neurodiversity? So, or perhaps the tendency of some of our colleagues in architecture who might also be neurodiverse to be inclined to this kind of more brutalist architecture?
Yeah, no, it's no, again, there's a lot of these things are great questions, and no, we haven't done that, but I have wondered about doing that. And it's more interesting in that, like, a lot of the work we've done, it's not such a pressing question. But here, where we've got a flashing arcade, which is overwhelmingly stimulating, versus a kind of peaceful path, we might find there are really strong differences if someone is on the autistic spectrum disorder. That they might be more reactive or react differently to spaces. We don't know. We haven't run those studies. So now we've got a stimulus base. We could go after looking at things like that. And I've wondered about in this stimulus set whether we could look at exceptionally wealthy people. It's not so hard to find in UCL students who come from wealthy backgrounds where they've been on holidays to the Maldives every other year. And it's very boring seeing a Maldives holiday, or someone who's grown up in a deprived council estate in London where a lot of the depressing footage is extremely familiar to them. It wouldn't be surprising. And I think you would find different effects of these different groups. But the architects, we haven't done it, would be interesting. I think we don't know whether they'd be more, what would be interesting is, are they more consistent than non-architects, or are they just as diverse? And it would be interesting to look at. The other group we excluded were video gamers, people that spend a lot of time playing first-person shooter games, because we assume when they go into these movies, they're thinking, yeah, that looks like, a lot of our movies look like things you might get out of these games that they would use as an exciting scenario to kill people, a lot of these first-person shooter games. So the context matters effectively. With the people we scanned, we kind of assume and did debrief them and say, does this, what was your experience here like? And they weren't saying, oh yeah. And they're all quite consistent in their ratings. They're not finding the brutalist architecture really positive. I didn't talk about it today. I'll just end on by commenting there was a study around 2018 we published on showing a set of photographs of different images of spaces and paintings to painters, architects, and sculptors to see how they reacted to different images and how they would transform them. And you could tell who was an architect or a painter or a sculptor from the language they used, just the linguistic features. The architects are much more interested in movement through the space, whereas the painters were interested in the foreground and the background of the image, and their training clearly had a strong impact on how they perceived an image, whereas non-experts are just quite boring on average. So architects do have a kind of, it's unsurprising, but it was very interesting to see the way they would conceive of a space differently to a painter who spends their time thinking about space as well. But yeah, there's a lot of exciting questions to follow up in all this research, and thank you very much for having me for this period, for this conversation.
Thank you very much for your time and also for sharing your knowledge with us. This was a very enriching session. So best wishes.
Thank you very much. Take care, Maria. Bye-bye.
Bye-bye.